Okay, this is the first lecture about the battery, and battery usually is used for backup power. Okay, I said backup power. That is because basically we are not discussing about the um, the the only power source of your equipment. Basically, we are not talking about that. Basically, we are talking most of the time. We're talking about the the storage system, energy storage system. Okay? Because this is the thrust of the development of the rechargeable batteries. Okay, so we will talk about the energy storage and why we need the energy storage. And then we will discuss about different categories of the rechargeable batteries, including different batteries and lithium-ion batteries. And then we will talk about the characteristics of the rechargeable batteries. And then we will talk about a little charging circuits. Okay, why we need the energy storage? The story comes from the renewable energy development. And in this chart, you can see the hydropower here. Basically, for the renewable energies, most of them are hydropower. But you know, because of the environmental issue, the most of the potential hydropower has already been exploited. So we cannot expand the hydropower to any further, basically. So if we talk about renewable energy, we have to talk about different sources, and especially we want to talk about the wind. Okay, and this is the wind power. Okay. You can see the growing of the wind power, and then you also can find the solar PV, the solar power here. Okay, so the most important two renewable energy sources are wind and the solar. However, you know, we cannot control wind, we cannot control the sun. So they are unstable. Because of their unstable nature, so we need the energy storage system to make them smooth. Otherwise, our power system cannot afford the unstability of the renewable power. Okay, and then there is another source here. You can see the CSP. CSP is called concentrated power source. Concentrated solar power. This is called the CSP, and later we will talk more about the CSP. And the CSP basically is to concentrate the solar power, and sometimes it can be stored temporarily. Okay, and the CSP here you have to find here, just a little here. Okay, this is CSP. And basically, in this chart, the pumped hydropower is not included. You know, there is pumped hydro. You know, the pumped hydro actually we have a pool on the mountain, and when we need the power, we can use water in the pool to generate the electricity. And when we don't need the electricity, or we can say the electricity is too much, there are surplus of the power, then we can use the power to energize the pump and pump the water back to the pool on the mountain. That is pumped hydro. And the pumped hydro is not included in this chart. And then the energy storage capacities, there are three kinds of energy storage here. The first one is thermal. Okay, this is thermal, and then that is the energy is stored as heat. And then when we need power, then we can use the heat to generate steam, and the steam will push the turbine, and it will push the generator and get the power. Okay, so this is thermal, and the second one is electromechanical. That is the energy stored as kinetic energy. Okay, that is electromechanical here. And of course, we focus on the electrochemical. This is electrical, chemical, electrochemical. Electrochemical basically batteries. Okay. And this is the so-called concentrated solar power. And this system is cooperated with thermal energy storage. You can see the sunlight here, and this is the so-called heliostat. The heliostat is mirrors. They reflect the sunlight to here, and there is a furnace here. The furnace here. Okay, so it will heat up the fluid here inside the tube. Okay, and then the heated fluid will come here. This is pump. Okay, what is this? Is number 6. Number 6 is a steam generator here. When we need the power, then the heat can come to the steam generator. Then basically this is water circulation, and here we can generate the steam, and the steam will push the turbine, and the turbine is coupled with the generator. Then we can have the power, electric power, then connected to the transformer to the grid. Okay, so this is the CSP system with thermal energy storage. So we can store the energy temporarily as heat here, and when we need them, we can transfer them to electric power. Okay, there is some notes about the CSP. In the CSP power plant, the system with include the storage. The solar energy is first used to heat up the fluid there is a molten salt or synthetic oil, and they stored in the insulated tanks. The insulated because it means it can insulate the heat transfer with the environment. Okay, and if we need the power, then the hot molten salt or oil is used in the steam generator to produce steam to generate electricity by the steam turbine generator. And so the CSP with thermal energy storage will not like the common solar PV or CSP without storage. The power generation from the solar thermal storage plants, it becomes dispatchable. Okay, that becomes dispatchable. That means when we need it, we can use it. When we don't need it, it can be stored. Okay, it becomes dispatchable and self-sustainable. Like in that day, the operation just like the coal or gas-fired power plants. Okay, and this is electromechanical energy storage. Basically, the system is like a flywheel. The flywheel is this one. Okay, this is a rotor, and basically okay, I forgot the term. Really, I forgot. You know, the flywheel, the rotor here is rotating. It will rotate, and rotate because if you the rotation of the rotor basically can store a lot of kinetic energy, and when we have to store the power into the rotor, then we can use electricity here and build the bidirectional converter. Why we need the bidirectional converter? Because the electricity have to come from the grid to the flywheel system, or from the flywheel system back to the grid. So we need a bidirectional converter here. And when we need to store the electricity, then the power comes into the flywheel system, and this is MG set. The MG set means motor and the generator set. So the electricity here, and this behaves like a motor, and the motor will provide the torque to the rotor and speed up the rotor. So the rotational speed will be increased, so the kinetic energy increases. And the whole system is enclosed in the housing. The rotation speed actually is very high, and there will be the friction, the air friction, or called windage loss there. And we want to reduce the windage loss. If we want to reduce the windage loss, we have to make the air pressure inside the housing to be reduced. So we need a vacuum pump here. Okay. And also, there are bearings because we have the axis here, and the axis have to be fixed onto something. And there is a thrust bearing here and here. And we also have to reduce the friction of the bearing. So there are some researches about the mechanical floating system. That means there is no physical contact between the bearing of the axis and the outside fixed point. We can use magnetic floating system, so the friction can be reduced. Okay, this is a flywheel system. Okay, and when we need electricity power, then we can behave the MG set as a generator, and the kinetic energy here will be transformed to electricity and via the converter back to the grid. Okay, this is a flywheel system. There are some researches on this kind of system, but yes, in Taiwan we have very few research on here. But I know in some countries like Japan, they have some researches here. And okay, we still focus on the electrochemical energy storage, that is battery here. And for the battery systems, if we use the battery as energy storage and work with the renewable power plant integration, we can do the ramp rate control. That means if we want to increase the output of the solar or other renewable energy systems, we want to increase the power. The power cannot be increased suddenly at a very large amount because the grid, the power system cannot afford the sudden increase of the power. Okay, so we have to use a ramp rate control. Ramp rate control means if you want to increase the power, then you have to increase at a reduced slope, at a reduced rate. And on the other hand, when you want to reduce the power output of the renewable energy, you have to reduce it gradually. You cannot reduce it suddenly. Okay, so that is called ramp rate control. And then the energy shifting. Energy shifting means yes, if you don't need it, then you can just store it, and you can release it when you need it. Okay. And then the smoothing. Smoothing is just like the ramp rate control. You have to smooth the output of the renewable energy. Okay, you cannot suddenly change the output of the renewable sources. And finally is the capacity forming. Capacity forming, that is for some systems, the renewable power sources have to guarantee at some time I have to output some extent of power. You have to guarantee that to the power system operator, and because you want to guarantee it, you have to install the energy storage system with the renewable sources. Then you can promise a certain amount of power to output at a certain time. Okay, this is called capacity forming. And then if we use the energy storage with hybridized thermal power plant, for a thermal power plant, for the power plant, they need the power itself because the facilities or equipment inside the power plant, they also need power. But before you generate power, you need power yourself. Okay, and for usually in the power inside the plant, they are supplied by diesel generators. Okay, they need diesel generators to supply the power. Okay, this is called a black start because you want to start power plant but you need the power, and the power you have to be from another source. And now we can use the energy storage to serve as a power source. Okay, and then we can also do the AGC function. AGC means automatic generating or automatic generation control. That is, you have to control the output of the power plant. And then the distributed microgrid. For the microgrid, maybe we have the power sources here, okay, and we have the load. We have load like EV and others, and factories and some residences. We have the load, we have the sources. But if we hope the microgrid can what's that? Can do the autonomous operation by itself, then they need enough power sources to supply the load. And when the supply is surplus than the load, then the power also have to be stored. So we also need the energy storage here. And for the grid control, okay, for the grid control, we have to do the frequency regulation. The frequency regulation, when I was a student, I wondered one question. You know, for the whole power system, we have the generators to supply power. We also have different kinds of loads. And basically, if we don't have energy storage system, the power generated have to be consumed by the load. Okay, but you know, this is very difficult because the load variation is very fast. Sometimes you turn on the light, sometimes you turn off light, or the AC conditioner. The power generator operator, they do not know what happens on the load side. So why there can be the equilibrium between the supply and the load? Why? When I was a student, I wondered this question for a long time. But after that, I realized something, because most of the generators, they are synchronous generator. For the synchronous generator, they basically has a large rotor. Okay, and because the rotor just like the flywheel we just introduced. So basically, the rotor can temporarily store the energy. That means if now the generation is higher than the load requirement, then the rotor will be speed up. Otherwise, the rotor will be slowed down. Okay, and what does that mean? That means when the power is too large, when the power supply is too large, then the grid frequency will be higher. Because the generator rotor speed is increased, so the frequency is higher. So you can see the frequency of the grid basically represents the situation of the balance between the supply and the load. Okay, but for a stable power system, we hope the frequency variation should be reduced. In Taiwan, basically the frequency is 60 Hertz, basically 60 Hertz, but there is some variation. But the variation will be limited between like 59.5 to 60.5. within the 1 hertz frequency or even lower. But in some unstable power system, the variation may be large. Okay, and anyway, the power system operator, they hope to reduce the frequency variation. So they also need some frequency regulation function here. And how can achieve the frequency regulation? Again, by the energy storage. Okay, and because of the frequency variation is very quickly. The variation is very quickly. So only the electrochemical energy storage can support this function. You know, the electromechanical system, the time constant actually is very large compared to the battery. Okay, and the thermal energy system, again, the time constant is very high, so they cannot respond so fast. Only the electrochemical energy storage can do that. Okay. So I also want to talk about the operating reserve. The operating reserve here, we have 3 kinds of reserve. The first one is frequency response reserve. This is the quickest, this is the fastest one. When the failure occurs, it has to respond in no time. Okay, and then followed by the spinning or non-spinning reserve, and then the replacement reserve. Okay, the operating reserve here, the generating capacity available to the system operator within a short interval of time to meet the demand in case of the generator fails or any other disruptions. Okay, so well, for the power system, you always have to face the fails of something and some disruptions from the environment. You know, sometimes the grid is disrupted by the typhoon, by the flood, or something. So they always have to face that. And then I'll talk about what are they? What are those reserves? First is the slowest one. The slowest one is the replacement reserve. The replacement reserve is the reserve power provided by the generators. Usually, the replacement reserve is provided by generators. Okay, they can only be provided by generators, and the generators, they need a longer startup time, like 30 to 60 minutes. What kind of generators can be started up in 30 to 60 minutes? Basically, they are natural gas powered generators. Okay, or the natural gas unit can be started in shorter time. If the power, like for example the nuclear power, maybe you have to start for many days, and for the core generator, it may take 1 day to start up the system. For all your system, maybe a few hours. But the natural gas is fastest for the from the fossil energies. Okay. And the replacement, why we call it replacement? It is used to relieve the generators from providing the spinning or non-spinning reserve until the operating reserve is restored. Okay, and then this is the fastest one. The fastest one is a frequency response reserve, and it is provided as an automatic reaction. Okay, it can also be automatic. It requires no human to intervene the operation of the frequency response because it needs a very fast response. Okay, so it should be automatic reaction to a loss of supply. And it occurs immediately following the loss of supply, and the generators will slow down due to the increase of load. As I said, if the load increased, water supply is not enough, then the generators will be slowed down, so the frequency will become slow and the frequency will become smaller. Then the frequency response reserve have to be cut in to supply the power to restore the frequency. Okay, this is the so-called frequency response reserve. And then this is a spinning and non-spinning reserve. The spinning means the reserve capacity is already online. Okay, this is so-called spinning. And the non-spinning reserve is the generation capacity is offline. Okay, so for the spinning reserve, the online reserve capacity is already synchronized to the grid system. Usually we will say the generator or the generation capacity it should be synchronized, because you know the power voltage or power current is sinusoidal. Okay, and we have to synchronize the supply and the grid. Then we can parallel the generation capacity onto the grid. So usually we use synchronized. Okay, and the spinning reserve already synchronized to the grid system, but they do not supply power. They already synchronized, but do not supply power. And when we need the spinning reserve, they can be supplied. The power can be supplied to the grid within 10 minutes from the dispatch instruction by the ISO. ISO means independent systems operator. Okay, they will give the command to the reserve system, and they will respond in 10 minutes for the spinning reserve. Okay, and for the non-spinning reserve, basically is offline and not synchronized, but after receive the dispatch this instruction, it also has to be to respond and to synchronize the system to the grid within 10 minutes. Okay, the same. But the difference is one is already online, the other is not. And they have to maintain the system frequency stability during the emergency conditions or the unforeseen load swings. Okay. And then in this figure, it shows the energy storage installed capacity. And the capacity here is, you can see the capacity is megawatt. Megawatt means this is power. This is power. This is not energy. Okay. From the chart, you know or we can say here this is a cumulative storage capacity, and this is cumulative renewable paired storage. So the difference between these two charts is, okay, the upper one is the storage capacity, and the lower one is a storage capacity paired with renewable energy. Okay, this is solar storage, and this is storage with renewable energy. Okay, and you can find that in the chart, in both charts, for the number 1 to number 7, basically they are the same. Okay, that means the first seven countries, they basically most of the storage capacity is paired with renewable energy. Okay, and then you can see the Germany and Morocco, and then South Korea and Israel and India there. Okay. And then this shows the installed energy storage by different technologies. The technologies are electrochemical, electromechanical, and thermal. Okay, and you can see the electrochemical. The top one is the US here, and also electromechanical. The first one is also US, and then you can find Australia, China, Japan, Germany. They are the top countries for the electrochemical storage. And then you can find UK, the electromechanical, and you can see Spain. Okay, the Spain they use the thermal cumulative storage capacity the most, and then the South Africa and Chile and the Morocco. Okay, and in this chart we can this chart shows the U.S. primary energy consumption by energy sources. Most of the energy used in U.S. they are petroleum and natural gas. Okay, they occupy almost 2/3 of the power consumption, and then here is the renewable energy, only 12% here, and within the 12%, you can see almost 40% is biomass, and then wind power, hydroelectric, and the solar and the geothermal. Okay, this is the situation in U.S. How about Taiwan? In Taiwan, the thermoelectric, this is thermal. Okay, yes, this is thermoelectric. Okay, this is thermoelectric. What is thermoelectric? Thermoelectric includes the petroleum, includes the coal, includes the natural gas. Okay, so these are thermal. Okay, these are thermal. So in Taiwan, most of the power comes from the fossil fuel. Okay, and then the second one is the nuclear. This is a nuclear power, but this chart only to 2019. Okay, and then you can see the pumped hydro. Pumped hydro is the blue one, and the renewable energy here. So as you can see, there is a long way to go for Taiwan's development on the renewable energy. But we can say within these 2 years, I mean in 2020 and 2021, the growth of the renewable energy actually is very large. Okay. Okay, here the renewable energy in Taiwan here. This is a percentage. This chart only shows the percentage, not the real amount. You can see the hydroelectric. Okay, the hydroelectric here. You can see one fact that in 2020 the percentage of the hydroelectric reduced a lot. Why? Of course, it's not because the reduce of the hydropower. That is because the increase of the other renewable power sources. And the increase is what increased most. You can see the solar. Okay. Actually, in Taiwan, we hope to achieve 20 gigawatt in 2025. 20 gigawatt. And do you know how much we achieve now? Less than 10 gigawatt. Okay, so we have more than one half to achieve. And here is another thrust for the batteries. That is the electric vehicle. Okay, for the vehicles, you can see we see this chart. Okay, in this chart you can see the BEV. BEV means pure battery EV. Okay, the only power source is the battery. Okay, so it needs a lot of battery in the EV, and then you can see the PHEV. PHEV means plug-in hybrid electric vehicle. So it can because it's hybrid. Hybrid means you can use electricity. You can also use the combustion engine. Okay, so here you see this is China's BEV, and this is PHEV, and this is Europe the BEV and the PHEV, and this is the US. A large amount of cars, a large amount of electric vehicles are produced and used in China and also Europe. You know the North Europe countries, they have a larger percentage of EVs used in their countries. And the power demand by the vehicle mode. Okay, you can see at first the cars and the vans, the percentage is lower, but now the cars and the vans, they have a lot of percentage here, and then the buses and the others. Okay, for the battery development, first we use the batteries for the portable devices like your cell phone, like your laptop, and then the batteries are used for the transportation. They use in the electric bike, electric scooter, and then electric cars, and then electric trains. Okay, for the transportation, of course, the battery storage should be larger than the consumable electronics. And then we will use the batteries for the energy storage. For the energy storage, the energy required is calculated by the megawatt hour or something larger. Okay, so the battery required is much higher here. And so for the development of the battery, the higher voltage is required, the larger capacity is required. Okay, for the batteries, there are some definitions we have to declare about. The first one is capacity. Okay, the first one is capacity. The capacity used here is ampere hour. Basically, the so-called capacity. The capacity is referred as the energy. We are talking about energy. And you know, for the energy unit, we use joule. Okay, basically we use joule, but joule is too small for us. So maybe we have to use volt times ampere. You know, volt times ampere is watt, and then watt times second is joule. But I say that is too small. So maybe we have to use volt times ampere times hour. That is better for us. But for the battery, usually we think the battery voltage is almost constant. We say quasi-constant. Of course, we know it is not constant, but the variation is not too large. So we just think that the voltage level is constant. So although we need the energy unit, we just omit the volt here. We just use ampere times hour. Okay, so ampere hour, actually, you know, this is a unit for electric charge. If we times the current with some time, then we have the charge, electric charge. So basically, ampere hour is an electric charge unit, but we use it as an energy unit. Okay, but ampere hour sometimes is too large for your equipment. So in your cell phone or your laptop, you can find the capacity unit as milliampere hour. Milliampere hour, of course, is 1/1000th of the ampere hour. Okay, the second one is the initial full capacity. We use a symbol as QF and a star there. This is the accessible capacity of a new battery. So initially, the battery capacity is the largest. Usually, it's the largest. Okay, for the new batteries. And then after you use the battery, we say you use a larger cycle, some cycles. After the charge and the discharge cycles, the capacity will be reduced. And here, this is the existent full capacity. The symbol is QF, and this is so-called ongoing maximum accessible capacity. This is a capacity you can have now, but maybe the capacity is a little smaller. Maybe the capacity is smaller than the initial full capacity. Okay, so you know the symbols, and then the capacity at present. The capacity at present means maybe you have fully charged your battery, and then you use the battery for a few while, and then the capacity will be smaller than the current maximum capacity. So that is capacity at present. Okay, then we have to define the two important concepts in battery technologies. The first one is state of health, or shortly SOH. The SOH is defined as QF over QF star. The QF star is the initial, and the QF is the existent or the ongoing maximum accessible capacity. Okay, and usually we use them as a percentage, so that times 100%. And the second one is state of charge, or SOC, and the definition is QE over QF. So, for the SOC, maybe if you fully charge your battery, then the SOC is 100%. And when you use up all the energy in your battery, then the SOC will become 0%. Okay, so now the battery will experience 0%, 100% SOC in short time, but the SOH, for the SOH, now maybe the SOH of your battery maybe 90%. If we say 90%, that means if you fully charge your battery, then the maximum accessible capacity is only 90% of its initial state. And usually SOH decreases as your used cycles. Usually. Okay. When we use a battery, we will define the end of discharge. Okay, the end of discharge or cutoff voltage we see here. When we use the battery, when we cannot use the battery anymore, I mean, when your cell phone, it will tell you the SOC is 0%, so it has to shut down. How does it know? How does your cellular phone knows the capacity, the SOC now is too low, so we have to shut down? Basically, it depends on the battery voltage. Okay, basically it's the battery voltage. So when the battery voltage is too low, then it has to be cut off. So this is the end of discharge voltage. And when we charge the battery, usually we use the so-called CCCV charging method. The CCCV means constant current and then constant voltage charge. So we have to define two points. The one point is CV voltage. That means first we use the constant current charge and the charge to a certain voltage level. Then it will be transition or switched to CV mode. Then the charging voltage will be constant. And when the charging voltage is constant, then the charging current will be reduced. When the current is reduced to some cut-off current level, then cut off the charging process. Okay, so we have two specific points. The first one is a CV voltage level, and the second one is a cut-off current level. Okay, for the batteries, we also have to define C rate. When we charge or discharge a battery, we use the current, because like we use the constant current to charge or discharge a battery. So basically, we use current. We use ampere. as a charge or discharge unit. Okay, basically. However, you know, if I say now I charge a battery with 2 amperes, for example, but if I use a 2 amperes to charge a 2 ampere hour battery, that means the current is very high. But if I use the same 2 amperes to charge a 20 ampere hour battery, then the charging current is very small. What I mean is, when I use the ampere as a unit, as a current unit, basically you will not have a real understanding about the level of the charging current. So we want to relate the charging current level with the capacity of your battery. Okay, so here the C rate is, for example, if now your battery capacity is 1 ampere hour, then if I say I charge or discharge a battery with 1 C rate, that means the charging or discharging current is 1 ampere. Okay, and if the battery is 20 ampere hour capacity, then 1 C rate means 20 ampere. Okay, this is the so-called C rate. And for the C rate, we also can quickly understand that how much time is required to charge the battery to the full state. For example, now if I use a 1C current to charge the battery, then we expect the battery will be fully charged after 1 hour. And if I use only 0.5 C rate, then maybe it takes 2 hours. And if I use 5 C rate, then it takes only 1/5 hour or 12 minutes. Maybe if you heard that for some EV charging station, they said we can charge your battery within 20 minutes. Then you can quickly understand how much C rate it is talking about. Okay. And then I will start to talk about different kinds of batteries. I first mentioned about the lithium lead acid batteries and the nickel hydride, nickel cadmium, and the lithium ion. And then we will put a lot of effort on the lithium ion batteries. For the comparisons here, you can quickly see that for all the voltage level, for the voltage per cell, the lithium ion is around 3.7 to 2.5 volt. And for the lead acid, the voltage level is about 2.2 to 1.7. And for the nickel series, nickel cadmium or nickel hydride, the voltage level is lower, is 1.4 to only 1 volt. Okay, you can see the difference between the voltage level and the current. For the lithium ion, of course, actually there are many kinds of lithium ion batteries. So the current sink capability actually they varies a lot. Here it says 125 C continuous. We are talking about continuous, and that means in very short time, maybe you can use a higher current. And for the nickel cadmium, nickel hydride, it may be 1 to 2, 1 to 3 C. And for the lead acid, it can afford higher current. Okay. And the energy density. Basically, the lithium ion batteries has the highest energy density. Highest energy density means if we want to equip the battery with enough amount, how much weight it will occupy. Okay, of course, we hope the energy density is larger than if we want to supply the certain amount of power, then we only need a small weight. Especially, we can consider that in your electric vehicle. If the energy density is too small, then you need a lot of weight to convey the battery itself. That is not economical at all. Okay, so we hope the energy density to be as high as possible. Here, the lithium-ion battery has the highest energy density, and the lead acid has the lowest one. Okay, and the temperature, the cycle life. The cycle life, basically the lithium-ion batteries has medium cycle life, and the nickel cadmium has the highest cycle life here. And lead acid, basically the lead acid can be used in a few cycle life. The cycle life is very limited, and the number here is higher than 500 cycles. I have to say, this is lead acid gel cell. There are different kinds of lead acid battery, and for other kinds of lead acid battery, the cycle life actually is even smaller, is even shorter. And the environment temperature, the battery can be operated within a certain temperature range. For too high temperature or too low temperature is not good. It's not good for the operation of the batteries. For the lead acid, for the lithium ion, maybe within this range. For the lead acid, maybe a wider range, maybe. But for different designs, actually they are different. So in this table, actually you don't have to think the numbers to be serious. This is only for reference. We can just compare them, which one is higher, which one is lower. But the number itself, you cannot take it too serious. Okay. And the electrolyte leakage problem. All the batteries will suffer from the electrolyte leakage problem. That is, if you just put the battery there, maybe in a long enough time, the electrolyte will leak out of the battery. Okay, they all have the problems. The recharge voltage level. For the lithium, maybe the 7.3. For the nickel cadmium and nickel hydride, 1.4, and for the lead acid, a little higher than 2 volts. And the memory effect, we once know that for the nickel cadmium, it has serious memory effect. That is, if you discharge the battery to a certain level, then it will memorize the certain level as a 0 level. Okay, that is called the memory effect. And only the nickel cadmium battery has a serious memory effect, and all the others will not have the problems. And the self-discharge, the lithium ion has very few self-discharge rate. That is, if you just put the battery there, it will discharge by itself. So gradually the stored energy will be released. But this problem is very minor for the lithium ion battery, only 2% per month. And for you can see this, the nickel hydride, 20 or 25%. That means after 3 or 4 months, all the capacity will be released completely. Should we take a rest? I think we have to take a rest for 10 minutes. So we come back 2:40. Okay.